Hello everyone. Here we're going to do an equilibrium example where we have one of the forces applied at an angle. As shown in the figure below, a uniform beam is supported by a cable at one end and the force of friction at the other end. So it's not attached, it's just the force of friction. The cable makes an angle of theta equal to 30 degrees. The length of the beam is 2.75 meters. The coefficient of static friction between the wall and the beam is 0.42. And the weight of the beam is represented by W. Determine the minimum distance x from point A at which an additional weight 2W, so twice the weight of the rod, can be hung without causing the rod to slip at point A. So let's look at the forces being applied here. We've got the tension of the cable acting along in this direction. Because it's pushing against the wall, pushing the rod against the wall is then pushing back with a normal force Fn, and the frictional force between the wall and the rod is holding that end up. So it's applying a frictional force in the upward direction along the wall. And then we've got the weight of the being applied here, the 2W that's being applied. And so it has a weight that's pulling downward here at this location. And we have the weight of the rod itself. And so we can put the weight of the rod as though it's acting only at the center of mass of that rod. So right here at the center, we're going to draw the weight of the rod acting downward like that. So this is W, and this one is shown is a 2W. And we know then that this distance to the center of mass is the length divided by 2, because this total distance to B is the length L. So one way to think of this problem would be to put a pivot point here at B. And so the tension in the cable is holding that rod in place at that location, B. And then we would have the weight wanting to torque it downward, the extra weight, the additional weight, 2W, torquing it downward, and the frictional force being the one to hold it up. If we move that weight closer and closer to the wall, then it applies more and more torque because it has a greater moment arm. And that torque that it applies needs to be small enough that the frictional force can still support it. Support both it and the weight of the rod itself. And so the torque due to the frictional force at that moment arm of L from a pivot point at B needs to be able to counter the torque due to the weight of the rod and the weight of the block itself. And so it says determine the minimum distance at which it can be hung without causing the rod to slip. Because as we get closer and closer, then it means a greater downward torque and it would want to slip. So we're going to try and determine that minimum distance. But we don't actually have to define our pivot point at B. We can in fact put our pivot point wherever we want. And in fact, I'm going to define the pivot point here at A for our problem. So let's define that as our pivot point. This is going to be our origin, so an x equal to 0. We have a weight of 2W hung at a distance of x, the center of mass weight appearing at an L over 2, and the tension being applied over at L equal to 2.75 meters. So I define my axes this way then. This is going to be a positive y, a positive x, and a positive z in this direction. And therefore, I get my positive torques if I'm rotating in that direction. Right-hand rule, thumb pointing along the positive z-axis. I'm now going to take that tension and I can break it down into components. And so there's a component of this that is pulling the rod towards the wall, and it really then is what's creating that normal force. Because it's pushing it against the wall pushes back with the normal force. But I've also got a component that is acting in this direction. And so this component down here is a t cos theta because it's adjacent to the angle, and this component here is a t sine theta. It's opposite to the angle because I just translated it from over here. And this theta is 30 degrees, we're told. And so we'll notice that this is our tx component, and this is our ty component. It's acting in the y direction. And that's the only one acting at an angle. The rest are acting either fully in the x or the y direction. So I'm going to start off by looking at the sum of the x components. For that then, I've got a positive Fn because it's acting towards the right, and I've got a negative Tx. Those are balancing each other out, as I had already mentioned. So I've got an Fn minus T cos theta equal to 0. And that basically then gives me that Fn is equal to a T cos theta. Second, I'm going to look at the sum of my y components. And so I've got a positive frictional force, it's acting upwards. I've got a negative 2w acting downwards, and w, the weight of the rod, acting downwards. And then acting upwards, I've got that ty or t sine theta, and those are all equal to 0. In the case that I'm looking at a minimum distance before it slips, that means that I am looking at my maximum frictional force. And so this frictional force here then is my coefficient of static friction times my normal force. And I've got 3w. And I'm going to make that explicit over here. I'm going to say that this is equal to my Fs max. Okay, my frictional force equal to Fs max. And that's what allowed me to write here that it's equal to mu s Fn. Continuing then, I've got a negative 3w and a positive t sine theta. Substituting from above then, this is a mu s times a t cos theta from up above. And so I can solve for my tension T equal to 3 times the weight divided by mu s cos theta plus sine theta. Lastly then, I'm going to look at the sum of the torques. For the sum of the torques, then I've got this component that wants to torque upwards in the positive direction. I've got the weight that wants to torque it downwards in the negative direction. And I've got this one also wants to torque it, the 2w wants to torque it downward in a negative torque direction, so clockwise direction. And the force of friction is right at the point, the pivot point or the origin. So in fact, I'm not going to get any torque out of it, but I'll still put it in my torque. I can still put it in my torque equation if I want. In other words, what do I mean by that? I could say that my f of f is acting at a moment arm of 0. And so I don't bother with a sign because it's going to fall out or drop out. That term is going to drop out. Then what? I've got a 2w that is acting at a moment arm of x, and I've got a w that is acting at a moment arm of L over 2, and lastly, I've got a t sine theta acting at a moment arm of L. And those are all then summing to 0. If they balance out, they're in static equilibrium. So I've just substituted in for my T or my tension from up above. I can simplify by noticing that the W is going to cancel out from all three terms. And if I solve for X, I'll find that I've got this term. And so if I plug in all of the values, I'm left with a distance, a minimum distance of 0.796 meters. Any closer than that, and the torque due to that applied or additional extra weight of 2W, and it'll be too large for the friction to hold it up. And so it'll pull the rod off the wall.